So here we're going to look at the law of radioactive decay, and it looks something like this. If we have some radioactive elements, let's call that element N, and N naught would be the initial amount, then we can calculate the amount remaining after some period of time if we take N naught and multiply it times E raised to the power of minus lambda T, where lambda is equal to the decay constant. We'll talk about that a little bit more in a moment. T is equal to the time that has elapsed. So N naught, that is the initial amount of radioactive decay, radioactive material that we have. So the initial amount of the radioactive element that we started with, and then N without the subscript is the amount of the radioactive element that we have left after some time t, that's time with an m, let's just rewrite that, time t has elapsed. So that's our general equation. So the decay constant, let's take a look at that. This is equal to the natural log of 2 divided by t sub 1 half, which is the half-life. So the half-life, that's something that might be a little bit more familiar. T sub 1 half is equal to the half-life. The half-life of a radioactive element is the amount of time that it takes for half of it to decay. Let's take an example. If we have uranium-238, its half-life, its T1 half, is equal to about 4,456 million years, at least according to some experiments done at the Lawrence Livermore National Laboratory. And so MA is mega anoms. That's one way of measuring time, and we could also write this as 4.456 GA, or gigaanoms for billions of years. These two things are equal. So we'll just write them either way. And so if we want to know the decay constant, we can take natural log of 2 divided by that very large number. Let's erase the chalkboard here and do that calculation. So the value for lambda for uranium-238 would be equal to the natural log of 2 divided by 4,456. That's in millions of years, so 1, 2, 3, 4, 5, 6. We'll add 6 zeros, and this thing comes out to about 1.555. I think it has 4 5s and then a 4 times 10 to the minus 10 per year. So lambda has these very odd units of 1 over a year, and that's the reason. The reason for that is we're taking the natural log of 2 over this. And we could write this in any way we like. You can write it in millions of years. In the paper that I took this from, they actually calculated it in seconds, because that's the way they were doing their experiments. But we're going to use years because it's a little more convenient geologically. So what if we have the case where we have uranium-238 and we have an initial number of atoms that is equal to 100? Well, if we wait one half-life, if T is equal to 4.456 billion years, or gigaanoms, then the number of atoms we would have left, the N, would be 50. So we'd start out with 100. We've gone through one half-life. And so then after one half-life, we would have 50 left. If we went through 2 half-lives, which is pretty close to 9 billion years, then we would have about 25 left, and so the number of atoms would be keep being cut in half over and over and over again. And so you get a chart that would look something like this. If you have the number of uranium-238 atoms versus time, it would fall off something like this, an exponential curve, which again has already been described by the equation that we have written. So the number of atoms of uranium-238 would be the initial number multiplied by e to the lambda t. So let's do a sample equation where a calculation where we don't have an even number of half-lives. Let's let t equal 4.0 billion years, so 4,000 million years. So what would we have then? Well, we would have n is equal to 100. That's our n naught, the initial number of atoms, multiplied by e raised to the power of minus 1.555 0.54 times 10 to the minus 10 over years. That's our lambda. And then that would be multiplied by 4 billion years. So that's 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to squeeze all those in there. So this has, and that has units of years. Notice that the years, this is 1 over years, that's years, so those years would cancel. Even though I've written it down here, it's really a year that's sitting up there. So the years are going to cancel, and we'll be left with a pure number, and that number in this numerical example would be 54. Well, we didn't yet talk about what U-238 decays to. It decays to lead-206. We say that this is the parent, and this is the daughter product. And so let's erase the chalkboard and take a look at this equation again. So we said that we have the number of atoms that are left of the radioactive parent would be e to the minus lambda t. So the amount of daughter product would be the initial amount of material that we would have minus whatever we have left. So if this is what we start with, that's the initial amount, the starting amount of uranium-238, and this is what we have left. What we have left of uranium-238, then the amount of daughter product, in this case lead-206, would be that starting material minus whatever N is. So it'd be N naught minus N, or equals N naught minus N naught times e to the lambda t. And when you see this written in a textbook, usually the N naught will be factored out, and so you'll see that something that looks like this. Oh, that should have a negative sign there. E to the lambda t. And so in our case, when we found out that N was equal to 46, I think we're working backwards. We found out that N was equal to 54. We started out with 100 atoms of uranium-238. We ended up with 54 after some period of time, and then the amount of lead-206 that we created would be 100 minus that, which in this case would be 46. But you could do the calculation this way, and you should get the same answer. So what does that mean from a practical standpoint? Let's say we have a crystal of zircon. So zircon has the formula ZrSiO4. Zirconium has a charge of 4+, and uranium can also have a charge of 4+. And we could make this mineral called coffinite. Although we don't really have to make pure coffinite, we can have a coffinite component. If you just imagine bits of uranium concentrated material that is floating around here in this zircon crystal. So let's say we have a zircon, and in certain places within this crystal, the zirconium is replaced by uranium. Well, we can use the equation of radioactive decay to figure out how old this crystal is. So after some period of time, what we'll do is we'll just circle these. Let's say this guy and this guy and that guy and this guy have all converted to lead-206. So uranium has decayed to this fellow here. We can calculate the age by playing some games. Let's take a look at the equation we just wrote. The daughter product is equal to N naught times 1 minus e to the minus lambda t. We know the decay constant from experiment. We can get the N naught and the D by counting the total number of lead and uranium atoms that are here. So that means the only unknown would be the value for T, the time. So we could solve for time and figure out the age of this crystal. And this is why zircon is the gold standard for age dating crystals. It absorbs uranium. Oh, you might wonder, by the way, what about any initial lead? If the zircon crystallized with some lead already inside of it, would that not cause a problem? Well, it certainly would, and sometimes it does. But the case for absorbing lead it's pretty limited. Lead has a 2+ charge, and the radius of lead is much, much greater than the radius for zirconium 4+. So the charge is wrong, the size is wrong. But if you consider it from a Pauling's rules standpoint, the partitioning of lead into zircon is going to be very, very limited, while your zircon is going to be much, much happier absorbing some uranium. But even if you didn't like the case of lead 206, you could also look at other decay cases. You could look at the decay of U-235 or uranium-232. These decay to other kinds of lead. U-235 decays to lead 207. 232 decays to lead 208. We're getting a little bit sloppy here, but you can write additional equations where you can also calculate the time. And if all three equations give you the same time, then you probably have a pretty good age date on your zircon and the rock that contains it.